Welcome to our fourth QWebinar. Today we will have Maria Schuld. Thanks to her accepting our invitation. She is a quite popular speaker on quantum machine learning. She is also working partly in Xanadu. She will also mention about PennyLane today, and she is also professor in Natal, South Africa. I am Abu. I am from QWorld, and we are preparing this webinar together with Aga. And also today we will moderate with Ayşin. Ayşin is from Turkey. And under QWorld we have different channels. Ayşin is also take part in QWoman channel. And Aga is our head of PR and marketing. And I and Aga is also in QWorld. Aga is also helping to QWoman channel under QWorld. So previously we had Nathan and Ronald. Nathan talked about open source in quantum science. He was our first guest. And then we hosted Ronald de Wolf. And he talked about potential impact of quantum computers on society. Both videos are available on our YouTube channel. So you can also subscribe to our YouTube channel and you can watch more. So I would like to thank again to Maria and shortly mention about our agenda. I will shortly mention about the protocol of the meeting. And then I will talk about the QWorld. Then Maria will take the stage and then we will have the question answer session. So our protocol is simple. We should all should be nice. And if you somewhat see something not nice, some harassment, please just tell me and or Ayşin immediately, and we try to take care of it. So this meeting is recording. Later we will put also in our YouTube channel. And you shouldn't record this because we didn't ask permission of people. Also, please don't broadcast this meeting. Today we will have this Zoom meeting. Also, we are broadcasting to YouTube. So you can use the comment boxes in each part and we will also follow them. And we will ask these questions to Maria at the end. We also had, this time we had a lot of application. It was more than 350. And we also had like more than 40 questions. But this time we filtered some of the questions and we really tried to select the ones directly related to quantum machine learning. And we just filtered the general questions, maybe some classical machine learning questions or some general quantum questions. So we already have some 20 questions we will ask, and we can also collect more questions during the meeting. So QWorld is a global network. Like we formally, our idea started before, but we formally like active, let's say 6-7 months. We start basically from education, introductory education, and we try to just do more on open source software, science, technology, also open documentation. So we are not alone with the same aim, but our aim is just building a global quantum ecosystem. So here you see many details about us. Last time I explained more about this slide, but this time I will make it very short. So we have different aims, different channels, different networks. So QWorld is a big network of networks, and each sub-network we try to focus on some special focus groups, let's say. And among all, maybe these Q cousins are the most advanced one at the moment. So currently we have 8 groups around the world, and we are growing day to day. And our initial year, we did a lot of introductory education, and you see at the bottom, we delivered more than 600 diplomas, and we really visit 13 countries. And now we will use more online tools, and most probably we will reach more countries. So this is our motto, like we invite everyone to be part of second quantum revolution. But of course, this is more abstract, and its more concrete form is let's create opportunities for every potential interested person. So the aim is really reach this potential people, and then just create these opportunities to welcome them. And if they want, then they can join. So we are in the currently NISQ era, and there are many discussions also about this era, like what can be the benefits and what we can get. We are all expect some reliable and scalable hardware. There are still some people who are suspicious about this, but as a QWorld, we are sure about one thing: at least software is good enough at this era, and at least to use for the education. Because I remember in the past, these quantum computing lectures, they are usually like master level lectures, and they are more theoretical lectures. And usually there are 5 people, maybe 10 people. But now all these quantum softwares give nice tools. All these ideas becomes like touchable, practical, so we can really reach 10 times or 100 times more people. So education is the best invitation. I think whole history, I mean, education always make big changes. So QWorld also started education, and I think in this era, we put some big goals for ourselves, and it's really like for 5 years. Maybe it will be the middle of NISQ era, or maybe end of the NISQ era, time will show it. And we are saying, let's working basically 3 directions. First of all, we should collaborate at global level. There is already gaps between countries or regions, and we are beginning of a new field, and let's try to engage everyone from the beginning. Let's invite them to be the first passengers and not to miss these opportunities. We should also be careful about diversity. Instead of talking these diversity issues after 2-3 years, why not start from the beginning, just engage more women or people from disadvantaged or underrepresented groups. Also, this is a very good opportunity for juniors. We are not alone to saying this, and many people are also focusing high school students. And we are saying, let's give opportunity these juniors grow together with this NISQ era, I mean this new field. So we are simply saying quantum juniors for quantum future. So this is my short introduction. So if you have some more questions, you can always access from different channels with us. And now I give the stage to Maria. So you can share your screen, Maria.
One second. There we go. Great. I just move the panel. Oh, wait, 1 second. I think it cuts off the screen. Let's see if that is better now. So I'm almost there. I had that before when I click presentation. Okay, so you see there's a bit of stuff cut out on the right, but I'm sure it's fine. Great. Wonderful. Thanks so much for having me. I'm very impressed already by the QWorld network and everything I learned about it in the last week of preparing for this. And also for like the great preparation. I also already looked into the questions, a couple of questions that participants had. And I realized from the questions, lots of them were about careers in quantum computing. They were about how to learn about quantum machine learning, what quantum machine learning actually is. So I assume that most of the audience is not an expert in quantum machine learning and probably not even in quantum computing. And this is always a big challenge and reminds me very much of myself when I was actually still in high school, and I went to all the quantum talks in the city where I grew up that I could get my hands on. And I was always sitting in the audience and thinking, you know, I always was looking for the magic of quantum computing and of quantum physics. And the speakers were always giving very, very boring talks because I thought, like, wow, they're so fascinated about these little details. They should talk about the magic. And I often experience that people who are not from the field in webinars like this are also waiting for the magic, for quantum machine learning to be better than any machine learning in the world. And unfortunately, I think I have to disappoint you because This talk, hopefully, if it's successful, will kind of like talk about or show you that the big things that we see in the media might not be so interesting, they might not be so true, but that there are lots of very, very interesting things hidden in the fine print, and that quantum machine learning is really also a theoretical field that's just starting to be actually born. And then this talk is not only about quantum machine learning as a theoretical discipline, but also about PennyLane, which is a software framework coded for quantum machine learning, probably the biggest ecosystem at the moment that's out there. And I also thought to meet the different levels, a lot of my talks, I will show a slide of a concept and then show code for it. So those of you who code can actually probably follow the code better than the concepts, and also invite you, if you're a bit more advanced in coding, you've got your Python environments installed, to pip install PennyLane if you can find it. And if you want, you can also play around during the talk. Okay, long story short, I have a bit of a motivational introduction at the beginning, also for those people who actually want to know what's going on in general. In the widest sense of the term, quantum machine learning is just the intersection of quantum computing or even quantum theory and machine learning. And this intersection is very rich, and in all different parts of it, there's a lot of research done at the moment. So let me just line out the different ideas that people are having. I hope you can see my mouse. So a classic distinction is always to think about, is the type of data quantum or classical, and is the type of algorithm or the device that I use for processing classical or quantum. And then there's this strange field of where everything is classical. Now, this is not just normal machine learning, but this is basically using classical methods to understand quantum physics for classical machine learning. So for example, there are methods of using tensor networks that were developed to understand and calculate with quantum states for neural networks. Or there are methods of using neural networks to represent quantum states. So there seems to be, neural networks and quantum states seem to have things in common so that you can describe them very well. There's this field of where your type of data is quantum. So if, for example, it comes out of a quantum experiment, you measured something, you've got now a file with your measurement data. And now you can also do machine learning. So this would be classical machine learning for quantum data, so to speak. And here's a lot of, so in experiments, in quantum experiments, there are a lot of approaches to, for example, do quantum error correction with machine learning, or interpret, so to shortcut quantum state tomography with machine learning. So there's a lot going on here as well. So we find 2 or 3 papers on the archive in this field at least every day, or well, every week at least. Then there's this quadrant here where everything is quantum, and lots of people say that this is actually the future of quantum machine learning. What's happening here is we've got quantum data, but now not in terms of measurements, but actually the states of quantum data. For example, you have a cryptography experiment and you get your photons out. And now you can send these photons into a photonic quantum computer and can process them and do quantum machine learning on the quantum data. And this is very attractive. It's very, very complex field because often the quantum data is not there yet. We don't know how it really will look like in a couple of years' time. But it's very attractive because we know immediately that this is very useful, because it will always be better to do all the processing on a quantum computer and then measure out, because measuring is this complex process and is very resource intensive, than measuring at the beginning. So this will probably be in future very, very interesting. If you start a PhD, look into this, there might be a lot in here. What I will talk about is the remaining quadrant, and that is probably the most common definition of quantum machine learning altogether, which is how to use quantum computers to do machine learning. And the idea, or what kind of sparks this whole field, is that machine learning is actually not just done on normal computers, but has actually a lot of hardware devices that it relies on. So from the most basic ASICs, which are literally just chips that are special purpose hardware, to GPUs and CPUs, I mean big GPU clusters. So the question is, if we have now new devices, new computational devices with a slightly different theory on how they process information, what does that mean for machine learning, and in the bigger picture also for AI? Although machine learning and AI, you can use them often very interchangeably. AI is probably more the commercial side of machine learning, as you could say. And there are 2 different devices. So I would say there are the quantum devices that are those near-term devices that are currently being developed. So a lot of them you have cloud access to already. They're noisy, they're small, there's a lot of problems. As a quick remark, also to comment on the introduction, it's a very nice idea to say, okay, software is already here, we can rely on that, that's good. But those hardware devices, they are incredibly unreliable. So like it's so hard, it can take you half a year just to get reliable data out of them that makes any sense. And then afterwards you have just used 1 or 2 qubits, and referees of papers just tell you, okay, this is not enough. And so this is really a problem to get this to work. One day we will have the bigger quantum processing units that we all dream of, and that were kind of the models that people came up with actually in the 90s in terms of quantum computing. And it's a bit different to think about those full-blown quantum computers and those quantum devices. And this is really also a good distinction of quantum machine learning algorithms. If you find a paper that talks about doing machine learning with quantum computers, they might have very, very different approaches and a very different logic, and sometimes even use the same words in such a different way that you kind of like struggle to recognize that it's one and the same field. And that's due to the fact that there's, especially the early literature is often like using theories and methods from what I would call good old quantum computing. And then there's the near-term quantum machine learning, which is completely different. The good old quantum computing, quantum machine learning, and I've also started off with that one, would go as follows. It would open a machine learning textbook and would look into it, and would also open maybe a quantum computing textbook, look through that, and then it would think, okay, where can I use Grover in a machine learning algorithm? Okay, a neural network, can I turn this into a linear algebra solver and then use an HHL algorithm or something like that? So it's really trying to kind of like just apply what we know from quantum computing to machine learning, to often have the goal of speeding things up. And I personally, so this is now only an opinion of mine, but I personally got very, very frustrated with this approach, because it is not leaving the boundaries of how people think about quantum computing to go to machine learning. And I think that this is not a very fruitful approach. So in quantum computing, the currency that people deal with for the last 30 years, and this is slowly changing at the moment. So the way papers are written, the way that people argue, the scientific discussions are made, is always with proving that speedups exist. So you have to show that your new algorithm, your new quantum algorithm, that there is a provable speedup with respect to like at least the best other algorithm that we know of. So, and there are 2 problems with this. First of all, speed up is, you know, making things faster sounds great, right? But it's a very, very specific and very like abstract definition, actually. Speed up means that the runtime or the computational complexity of the runtime grows in a certain way faster or slower with the size of the input. So it often doesn't talk about how long it takes. So good old quantum computing would say, for example, if something takes 100 million years instead of forever, this is a good thing. But in machine learning, this doesn't work like that. If your neural network doesn't train, I mean, if it takes a year to train your neural network or a day, this is like a really, really big difference that makes things from impossible to possible. The second problem that I find with this quantum machine learning approach is this provable. So lots of things in machine learning are not provable. So for example, optimization, training is an NP-hard problem. You can prove that it's NP-hard. So for quantum computing, this is unsolvable, and it stays unsolvable for quantum computers as well. At least like in terms of global search. So most of what we do in machine learning is not provable, it just works. So basically I would say that the theories that we established, and they are brilliant and they are really, you know, they carry far, they don't carry for machine learning. So now let me come to then the near-term quantum computing, and you might have guessed that this is the one I will focus on now in the talk. Near-term quantum computing works completely different. You have a quantum device, you often, you know, maybe the device is part of a company or you're part of a company, and you have the task to find an application for the device. And you might recognize that machine learning brings you lots of money, it's commercially very viable. So you think about, okay, how can my device do machine learning? And the approach that I will talk about, which is the most popular at the moment, is to train your quantum computer as if it was like a neural network or a traditional machine learning model. So you basically do something like we know from quantum control. So you kind of like have physical control parameters that you update in feedback loops until your device, which kind of produces measurement results that you understand as predictions. For example, there's a cat or a dog on a picture. To optimize those until you have a machine learning model that can do its task very well. So this is like kind of what I will talk about. also here, you hear already, I'm a bit critical about everything here, but also here I start getting a bit frustrated over the years because now this is very empirical. So what do I mean by this? The papers, you know, run a little algorithm on a quantum simulator, and then they maybe run it on the IBM quantum computer that's out there in the cloud. And then they get some curve, and then they say, oh, this is faster than if we run a small neural network. But very often those results don't really tell you anything about the devices. They're very limited because they compare very specific situations in a regime that no one cares about, which is small data, a few qubits that actually run the computations. So I personally think there should be a third step, and this is something I'm very interested at the moment, and I'll touch upon it here and there because it's in the making, but is to develop a theory for quantum machine learning that is not the good old quantum computing theory, but that actually takes elements from classical machine learning theory and starts viewing quantum computing from that part. And I hope that I can give you at least an idea of why I find this interesting and what this should look like. And then finally, so you remember that I will also talk about PennyLane. So in this near-term quantum machine learning approach and near-term quantum computing in general, software is absolutely crucial. And software is actually a bigger role, it plays a bigger role than just, you know, being helpful to do simulations that we think one day the bigger computers will do. So it's more than just exploring. It's also actually a business strategy. So if you know Qiskit from IBM, to create an ecosystem for free, I mean, it's all open source, is also a way to like dominate the market and get to know, become a player. So a lot of communication is dealt in software. The company I work for, Xanadu, and I'm very involved in that, develops a software package for quantum machine learning in particular. So not at this stage, not for every quantum computation, although you could run every quantum computation, but what we have in mind is exactly this: training quantum computers. And so you have to think about this software, and I use it kind of to demonstrate a lot of things, but you have to think about it not so much as, you know, an end-to-end, one-size-fits-all approach, but it's actually how can I say, a building block that plugs into classical machine learning frameworks. You might know of softwares, frameworks like PyTorch, TensorFlow, but also something very simple as NumPy, and connects them to quantum computers. So PennyLane is basically a communicator between classical machine learning and the quantum device. And then you can build very, very big quantum classical machine learning pipelines with this software. So that's it for motivation. It took a bit longer just you know, to give you an idea of where we are. And now we get into the more nitty-gritty part. Since the audience is so diverse, I have to probably give a little bit of an introduction into machine learning just to understand what is actually the problem we're trying to solve. And this section, so the message in this section is very clear. What we're trying to do is we're trying to solve the problem of generalization. We're trying to solve the problem of like giving a machine very little data and making it understand, or making it like understand the patterns in this data to conclude what happens to unseen data. Those of you who do a lot of quantum computing now see the second one and think like, oh my gosh, not another introduction to qubits and stuff. But in the quantum computing introduction, I don't want to start from Adam and Eve, but just give you an idea of basically the maths that a simulator is doing. And I put also a lot of examples from PennyLane in there. So this is at the same time like kind of an introduction to PennyLane and how it's built. And then I get to this idea of training these quantum computation. And there are 3 topics. If I don't get to all of them, I'm not too worried about, which is how to encode data actually. So if you want to classify an image, is there a cat or dog on it? How does your quantum computer actually represent that image? And I think this is the most crucial part of quantum machine learning whatsoever. And then, you know, you can talk about actually what are the circuits that you can train then? And then in the end, how does the optimization work? So this is kind of the agenda. Okay, so there are 3 ingredients to machine learning that you always find in probably every machine learning algorithm. The first ingredient is data. Here on the left, you will always find, for the more like thorough people who are more mathematically inclined, you will find a bit more of the equations, and on the right side for everyone else, the pictures. And I will talk here or think here about the most basic problem of machine learning, which is supervised learning. Just as a comment, because there was at least one question about reinforcement learning. There's also a lot of theory more on the old-fashioned side, but on quantum machine learning with respect to reinforcement learning. But a lot of reinforcement learning is based on supervised learning. So, you know, the way agents can develop their policies and stuff like that. So it's good actually to first and foremost think about the most simple problem and the problem that's the most solved in machine learning, which is supervised learning. In supervised learning, you've got some inputs X here plotted for like, you know, just a single dimension. And there's some relationship to some outputs Y. And these could be like binary or like discrete values or like continuous values. So this would be a regression or classification problem. And so this data is given to you. In terms of code, I warned you that I would show you always PennyLane code for the quantum computing. For the classical part, I'll show you PyTorch code. And right in the end, there's one slide where I integrate PyTorch and PennyLane code. So let's see if we get there. So the data would, for example, just look like this. It will be X and Y pairs. And here you see this is just actually a linear fit, you know, a linear function between X and Y. The second ingredient to machine learning is a model family. And this is basically your ansatz or your guess for what is a mathematical function that maps from X to Y. And a very famous example of these mathematical functions are neural networks, for example, or back in the day, linear regression, like a linear model could be something like that. So here I plotted, for example, different linear models. Two things that are important. First of all, you see already here, this is the part that we will outsource to a quantum computer in the end. So we want this F to be computed by a quantum computer. And the second point, I forgot. Oh yeah, the second point is that not in all machine learning models, but in most of them, there are some parameters here. I always call them theta or phi or something like that. So basically, you don't actually define a model, but you define a whole model family that is parameterized. So for example, you could say my model family is a linear model, and my parameterization is kind of the y-intercept and the incline here of my linear model. In PyTorch, this would, I mean, I wrote up the most didactic, smallest example I could think of, but you can just define a function, which is your model. It takes like, this will be your theta actually in the example, and some data and just multiplies the two. So this is a linear model without even a y-intercept. And then the last and third ingredient of machine learning is always a loss function. And the loss function kind of compares what your model says about X. So what's the prediction of the model for like a particular parameter, and compares it with a target value. So, you know, in the picture, which is, for example, you can have the mean square loss where you just check what's the distance between like kind of what your function would say and what your data point actually is. And here I just coded this up. So you put two things in and you can just like compute like the mean square value, the absolute square value. And now you can actually already state, and we're almost done here with machine learning, is the goal of machine learning is to minimize the average loss of the model. And average is here in quotation marks, because what I actually mean is the expected loss. So for those of you who like equations, you integrate over all data that you could have, you weigh it by the probability of seeing that data, if you have that probability, otherwise it's uniform. And then you integrate over the loss function of your predictions and your target values. And what machine learning does is try to find the model that's the minimum of this expected loss. If this was a bit too much for you, which I can totally understand, then think about it in terms of this picture. What you see on this axis here are different models. So this is a family, and every theta is a different model. For example, theta is a different inclination of your linear model. And now you try to find the inclination of a linear model such that it minimizes a certain function. And what's that function? It's like your average loss, so the average errors you make on your data, basically. So low is good and high is very bad. And now you can say, okay, fine, easy to solve, right? I just like, I have some optimizer or something, and I kind of find these minima, and this is now my model in the end, like either this one or one here with this y-intercept could be the model that I want. However, this is obviously impossible. And why? Because check here, you have to get the true expected loss, you have to integrate over all data that you could see. So not the data that you're given, but any data that could happen, because the data you get given is only like a small subsample of the data that could happen. So you have to basically integrate over all images that could ever be made of cats and dogs. And you will immediately see that this is impossible even to think of or define this set very nicely. So what machine learning does is in practice is it actually minimizes something different. And this is the big problem of machine learning, that you actually minimize something. You want to minimize something you don't have access to, and you minimize something else instead, and you never exactly know like what's the relationship between those two things. So what you minimize instead is actually the average loss over all your data points. So this is your training loss, or you could also call it a cost, but cost functions are sometimes like used for having other terms as well, like regularizers. But yeah, so basically the quality, this green line here is the quality of your model on the training data. And now you can immediately see, so I mean, this is just a sketch, but it probably tells you something about reality, that sometimes your green lines, so the models you find that are minimal, are actually really good. So the neural networks that actually fit the data very nicely, or yeah, fit the data very nicely. But some of those very good models here, very low, are actually very, very bad in the real function that we want to get. So what does that mean? They don't generalize well. So generalization means basically that your training data, if you do well on the training data, you also do well on unseen data. So most of you might have know this phenomenon as overfitting. So for example, this here would be a model, for example, this model here that kind of fits the data perfectly well. But if I have unseen data, like a new data point here, I would do extremely badly. While this model here doesn't fit everything well, but it kind of like doesn't do so badly. I just wanted to add, like in the code here, this is like kind of the average loss. So this is kind of the loss now that we have access to. So you go over the data that you have, but this is just like for completeness. And then the last little bit, most of you know that the machine learning pipeline, but this is not so crucial at the moment, but it often like takes training and test data. So it takes the data set and splits it. And the reason for that is actually, you can now like understand it with this picture, is if you maximize or you optimize on the green function, but you want to optimize on the black function, how do you know that you're doing well? So you like have a bit of unseen data that you keep behind, and you hope that it approximates the black function a little bit. So if you're with this model, you would immediately see, oh, the pink function that I have access to, that's my data that I kept aside, is doing like very poorly. So that's machine learning in a nutshell. And let me just check. Oh yeah, I don't know if this is so important, but like now here I just added the optimization step. This is basically just to show you afterwards when we do the quantum stuff, it will look almost exactly like this, but we have here a quantum model. So that's quite cool. Yeah, so what did we learn, or what's the takeaway? So maybe I want to come back to a comment I made right at the beginning, why I think that traditional quantum computing is sometimes so limited in machine learning. So and mainly the reason is that we always talk about speed ups. So I understand that obviously to invest a lot of money into quantum computers, we have to make a good motivation that we can't do things classically. But in machine learning, the main goal is not necessarily first and foremost speed ups. The main goal is to kind of like solve this problem of like having this proxy optimization. So finding a good model that on the green line that performs well on the black line. So basically that a model that's trained on some data and performs well on unseen data. And that's called generalization. So I think the goal of machine learning is a generalization, but quantum machine learning for many years has just focused on speed up. So this is basically why I think we need a new type of theory that thinks about, can quantum computing do this well? Yes, so this brings me to quantum computing. So yeah, for those of you who know this well, they can now install PennyLane and then follow it. There's like, I use like slightly different notation. So this is here, I will draw quantum circuits here, I will draw the maths or like the linear algebra that's happening. And here, this is for people who really hate numbers. This is just like a picture. Quantum computing, as you all know by now, probably, most quantum computers rely on qubits. Actually, at Xanadu, we're building a quantum computer that can do qubits, but also higher order qubits. So to speak, like, so qubits that are not only have basis states 0 and 1, but 0, 1, 2, 3, 4 until infinity. So they're called continuous variable quantum computers. So this doesn't always have to be a qubit, but for simplicity, we will assume this now here. So I've got basically just like physical subsystems that can be in state 0 and 1. And the mathematical description, and by that I really mean, you know, you often see in talks like kits and bras, but this is a very abstract notation. What in the computer or in the simulator, so in basically if you have a classical computer that simulates a quantum computation, a quantum state is represented by 2 to the n dimensional state. And in this vector or this array, there are different numbers. And how do you interpret those numbers? If you take the absolute square of the numbers, it's the probability of measuring a certain state, so of measuring these qubits in a certain state. So here, if we don't have done anything, everything is in 0, this is very simple, because what does that mean? The probability of measuring 0, 0, 0 is 1, and everything else has 0 probability. So it's a deterministic state. If you do a measurement, always the same thing comes out of it. Then up here, you've got the Bloch sphere representation, which is also quite famous. It's not exactly this vector actually, but it's a representation of this vector in like a space. And quickly, why is it a sphere? Because the absolute square, so the length of this vector always has to add up to 1. Otherwise, you can't interpret this as probabilities. So this is kind of like the Bloch sphere representation. You can interpret like basically the probabilistic information about your quantum system being kind of captured in this vector. And now we start, looking into PennyLane code, and this is now PennyLane code that exactly expresses the picture that I had here now. Quickly, so I know it's like dodgy to import everything, but just for the sake of didactics, I do that. For now, ignore this first line. It basically just says PennyLane or any quantum computation always needs a circuit and a device that the circuit runs on. So this is PennyLane's way of defining a device. The device we define is just a default simulator that ships with PennyLane. So it's at the moment we're not using like IBM's chip or whatever. We're just using like the most simple version. And y is equals 2, it means that we have 2 qubits in this case. Why don't we call it qubits? But y is because we have these these other continuous variable quantum computations, and there we don't have qubits. So PennyLane can do the qubit version and also the continuous variable version. And now in PennyLane, so also ignore this line, it basically just ties the device to the function in which we now define our quantum circuit. So this is our quantum circuit. What happens in here is nothing. So because what happened here was nothing, we just have the ground state basically. But the quantum function, I kind of return something. I always have to return like a measurement or something. Because on a real device, you can't just like do a quantum computation and leave it. Like you would just measure it. And if it's not measured, you don't know anything about it. So what I return here is the probabilities of, basically the probabilities here, those ones here. And you see, if I run the circuit, what I get is the probabilities. I get 1, 0, 0, 0. So this is exactly this, basically this state here, if I take the absolute squares. And then if I can hack, so it's a bit of a hack because with real devices, with hardware, we can obviously not do that, but I can actually get the state. So I can not only get the probabilities here, but I can get this vector, which is in general a vector of complex numbers. I get to that just now. And you see, but here it's very simple. It's 4 complex numbers, but the first one is 1. So it's exactly the same in this case. Next step. So, and altogether, my point here is that quantum computers just do linear algebra, which will become important now in the last part. So now I can apply something which is a quantum computation, a physical circuit. We call this or we often have the symbol of a unitary, because we know every quantum algorithm will in the end just be a unitary evolution of some sorts. How do you do this in math? So how do you do this in your simulator that you code? You take the 1, 0, 0, 0 state and you multiply a complex matrix that has the characteristic that it's unitary, which is kind of a generalization of like an orthogonal matrix. So what happens now? Afterwards, you've got a vector where you have lots of complex entries, obviously. And what happened to your, if you saw here, what happened to your quantum state, it actually moved. So now you're somewhere else on your high dimensional Bloch sphere. By the way, this Bloch sphere is obviously just 2 or 3 dimensional in some sense. But if you have more than 1 qubit, you would have a very, very high dimensional sphere. So it's just an illustration. Now let's do that here. So what I do, it's a bit of a hack as well. I define now U, a unitary matrix. So this is, this matrix here. And there's a function in PennyLane that just, like pretends that, your algorithm is given by this matrix, which is called qubit unitary. In the background, it would decompose this qubit unitary into other things. And you see now my probabilities changed. So there I have half the probability to measure the state 1, 0, and half the probability is measure 0, 1. And my quantum state is like this kind of strange thing of complex numbers. And now the last thing is the measurement, what happens there. So in principle, if you now measure the qubits, so there are different measurements you can do, but the most basic one that most of the quantum computers do is it measures just the state. Is it in a state 0 or 1? And now every time you measure, you get a different bit string out of the quantum computer. Again, you can do that in PennyLane. What happened here, what changed to the previous example is now I don't have probability here, but a sample. So I take a sample of, this is now technical, the Pauli Z operator, which is the one that measures -1 or 1, so 0 and 1. And also on the second qubit. And I get a sample out. -1 and 1 means the first qubit was in state 0, the second one was in state 1. But still I have the same state vector. So what I want to show here is also that a quantum computer can really, so you can take different measurements and interpret the output of a quantum computer very differently. You can interpret the probabilities you measure, you can interpret samples, you can get expectation values up. This is now the next one and the last one. So here we had just a measurement, and you get, every time you get something different out of it, which is hard for machine learning because you want a prediction out. If every time your output is different, like it's probabilistic, it's really difficult, except from a certain class of models, but for the common neural network. So what you can do, you take a measurement and you average, which is called like a quantum expectation value of a certain measurement. And so basically, instead of like, you know, projecting the state onto like 1, which is this state, or 0, which is this state, you would kind of get a value in the end, which is the average. So if your quantum state vector is closer to 1, you would get a value that's closer to 1. If it's closer to 0, you would get a value closer to -1. And mathematically, what happens is that you get this like quadratic form here. So this is a matrix representing your measurement operator. And then you have to sandwich, so you have to like apply this other part here. For those of you who have seen the bracket notation, so Dirac notation, so this one here would be your ket, and this one here would be your bra. But I never understand why people actually use this in talks, because if you can't deal with that notation, you're already lost on the first slide. So, but it's completely, in terms of qubit, completely equivalent to matrix multiplication. So quantum computers are really linear algebra performers. Linear plus, this is a little bit non-linear, as you can see, so it's quadratic, but everything else is linear. And here we replaced just the sampling by xval, which gives you this expectation value, which is this average over measurement results. And you see you get 0, 0. What does that mean? It means that your qubit was kind of somewhere on this boundary, I guess, or it's 2 qubits, but so they're probably entangled, but like, so you will have a state that's neither -1 nor 1, so it's somewhere in the middle. And now I already mentioned that obviously in real life and real quantum computers can't just implement this big unitary matrix, and this unitary is really large because it's 2 to the n dimensional. So if you have 100 qubits, it's 2 to the 100 times the 2 to the 100 dimensional. So you can really not write this down. So in real life, what people, or what quantum computers do, they implement like very small gates, like local gates that only act on 1 or 2 qubits. And in the mathematical notation, you can just understand this as like lots of matrices that are one after the other multiplied with a state. And now if you do this measurement plus average thing, you again like sandwich it and get a scalar out. And this every gate kind of, you can understand, turns your vector into a different position, so to speak. And then here, what I just did, like, so now we're rid of this unitary, but this is now how a circuit could look like. For example, these are different gates. If you study quantum computing, you know them very well. You apply them to different wires, and then you get also like your output. So now we've got everything that the normal quantum computing textbook would give you. And now there's a very important observation. Most quantum computers depend on, or most gates, how they're implemented, they depend on physical parameters. So for example, if you have an ionic quantum computer or something, you could maybe shine a laser light or like some field, magnetic field or something onto your qubits and thereby change their state. But these fields, as everything physical, they're not discrete. They're not like on or off. They're somehow, you increase the magnetic field and you decrease it again. So in some sense, all these gates in physics, they're always dependent on parameters that you can tune. And Now this is important for machine learning because you remember what we had was, or what we were looking for was a parameterized model family. So we were looking for something where you put input in, you get some output out. We get output out here nicely. We've just shown with the measurement. If you average, you get like always the same number out. I mean, a number that you estimate with a lot of measurements, but now we wanted something that we can tune so we can optimize to find the best model. And it turns out most quantum computers are naturally like that. And here's a bit of an anecdote actually, or like something that I always find strange. If I go back 2 slides, most teams that try to build quantum computers spend sometimes 20 years to implement those gates here. So like the whole community always uses this Pauli X gate or a C0 gate. We know a lot about them. They're theoretically well understood. So what you do if you build a quantum computer, you try to make your physical platform implement those gates. However, in a sense, like we can learn an algorithm very nicely if you just give me access to basically the pulse of your laser light or something like that. So this is actually an observation that goes beyond quantum machine learning. It means like quantum computers, we can utilize, so if we think of computations as being something that's trainable or that's adaptable, instead of just, it's like discrete gates that I apply and I try to find the right order, then it's possible that we can, we can save our experimentalists and our technology a lot of trouble to implement those like discrete gates, because we could just say, give me a parameter and I train whatever I want. And there are papers out that train small near-term quantum computers, for example, to implement Grover's algorithm. So they kind of like compute the desired output of Grover's algorithm, and then they train these parameters until actually it does what Grover does. And it's quite interesting what's going on there. So in PennyLane, this would look like this. For example, you would have a gate, and very often you would just talk about Pauli rotations. So they're called Rx, Ry, Rz, and they kind of rotate this vector in this blosphere around axes. But you see here now, this gate has a parameter, phi, and the circuit takes a parameter. So now I can only call the circuit if I say what's the parameter. So, and this could be now interpreted as a weight. Okay, so yeah, this is what I was talking about. We can train these computers, so we can like kind of basically say define a cost on our measurement outcome, and then we can kind of like have routines. And if we get to the last part, I'll talk about it. But so this is extremely interesting theory, how you train those things, because we can actually define gradients of quantum computations that can be calculated with quantum computers. So there's a lot of active research there. So this is now a full PennyLane example that trains this circuit that we kind of constructed here. It looks very similar to like the Torch, the machine learning framework. So you define like your initial parameter phi, and then you define an optimizer. And for 5 steps, for example, you just like optimize this phi value, and these are the phi values you will get. And you see the circuit learns to make phi bigger and bigger and bigger. And the last thing about quantum computing is that I was kind of skipping over this device thing. So obviously, there are lots of quantum computers out there. And so PennyLane is, sometimes we get users who ask us like, it would be so nice if you had different devices. And I was thinking like, we should advertise this more. But PennyLane, you can use whatever device you want in it. For example, you can run your circuit on Qiskit quantum computer on the hardware. So you can even have a cloud access where you run your device on the real quantum experience. And also to other like vendors, and there are lots of more coming that are programmed or coded up at the moment. There are also community plugins done by other people than us, which is quite cool. So it's growing. And how you would now call these devices, you just change this name here in the first line. And you could even make 6 different devices and run 6 different quantum computations and kind of like combine the results or something like that. So there's an example that we have to really think bigger in quantum computing. It's not just this like one computer, but it's a pipeline. It's really a big thing. Let me just check how I'm doing with time, because now okay, yeah. I know I spent a lot of time in the foundations, but I hope now you're equipped to understand what I want to say about machine learning. And the message is actually not so difficult now, I hope. So it's this idea, as I said, in near-term quantum machine learning, to use a quantum computer as a machine learning model family. So, and there are 3 steps. And basically, so I have spoken about the processing step in some sense. So because I said we can kind of like train gates in a quantum computer. I also spoke about measurements, and we can just interpret basically the measurement results that we got from averaging over lots of measurements. So we get a number out, and we can say this number, if it's larger than 0, it's a cat. If it's smaller than 0, it's a dog. But what is actually a cat or a dog? You have to encode data into your quantum computer. Otherwise, how can it predict what's happening with this data? So I'll speak mostly now about the data encoding, and then maybe a little bit about the processing and the optimization. And as I said, this is now, so forgive me because I'm really opinionated there. I think that the data encoding is really important. I want to convince you why, actually. So let's now write this quantum computation down a bit bigger. We talked about like this model circuit that's trainable and about the measurement. There could be some post-processing afterwards, but now the encoding step. And the encoding step is just another quantum algorithm. And you can just say, like, instead of encoding trainable parameters, why don't we just encode our features? And our features are, for example, the values of the pixels in an image, or I don't know, frequency values of kind of like signal processing, or whatever your data basically is. And it's interesting or important to note that in the simplest way, this data encoding is part of every quantum algorithm, because even if you do Grover search or Shor, you always have to encode an input, right? Like, and usually this is just a bit string. So this is the usual way it's done. Your X is like a bit sequence, like 101. And then you just like flip qubits if there's a 1 in your bit sequence, and you do nothing else. So the quantum circuit, so this is now the quantum circuit, sorry if I go back, this is this SX, for example, for a certain type of encoding. And what you prepare your quantum computer in is this state here. And you could definitely do that in quantum machine learning as well. There are some theoretical reasons that exceed what I'm talking about here to say this is maybe not a very good idea for generalization. So it's not a good idea. It's interesting also, sorry, but like it's actually an easy, so this is a very good example why you have to be careful. So this is a very easy encoding routine that gives you a lot of power, because you kind of map data into these like large basis states, so which live in high dimensional spaces. But what it's bad at is generalization. So it's again like an easy trap to fall in. There are lots of other encoding routines. So at the beginning of quantum machine learning, people have thought about this one here. So I don't know. So now I'm using Dirac rotation, although I was speaking against it. But what actually happens is that the amplitude vector that I was showing you a lot of times earlier, so this really high dimensional vector where you read the probabilities out, you could also just associate that with your data. So if you've got, for example, you have an image, you like kind of turn it into a vector, and then you just apply gates to your quantum computer until the probability distribution kind of mirrors your inputs. So it's a bit of a crazy way. So what you do there, you kind of encode data into probabilities or into amplitudes, which are the absolute value squared is the probability. So this one here is also kind of interesting, but in the end it's you know, like you work quite hard to get the state. And then in the end, you can only apply like gates to it, and it's not entirely clear where the power of that lies actually. You could also like encode your inputs x1, x2, x3 into these rotation gates. And there could be like really big, big routines that are your encoding steps. So this S of x can be basically anything. This one here is an example from an IBM paper that proposes this as a feature map, which could be an intractable feature map. It could be lead to quantum so-called supremacy. But only my comment here is also like that good software kind of abstracts these things away from you. And for example, in PennyLane, you can, most of these feature maps are just a one-liner. So you just feed in your data into like a function, and that function does the whole decomposition of these circuits for you. So don't be scared of those things. I think we have to theoretically understand them, but from a software perspective, they are not very complicated. And now the two comments why data encoding may be the most crucial step. And I'm really on a mission, like, because I think this is, for me, this is the key to quantum machine learning, but other people might think completely differently. And I can't go deep into this, but I just want to give you a taste of it. In classical machine learning, an entire theory that was very big in the 90s and is kind of the alternative to neural networks, so big theory about kernel methods, works as follows. And this is now how it mathematically works. So the algorithms will work a bit differently. Mathematically, you map your data, X, your data points X, from the original space, for example, the space of images, into a really huge sometimes infinite dimensional so-called feature space, which is reproducing kernel Hilbert space. So it's a Hilbert space. And now you analyze your data with linear algebra in this feature space. And why is this super interesting? Because this is exactly what data embedding into quantum computers does. So if I go back quickly, what this whole algorithm does, it prepares a state, a quantum state that is 2 to the n dimensional, so exponentially large, that depends on x. So basically, this thing that kernel methods in machine learning are based on is what every quantum computation does automatically the moment it encodes classical data. So this is important because it gives you a very easy link. So for me, quantum computers are really just kernel methods of a very specific kind, and it's interesting to work that out. Most young people, well, young people are also young, but like most students just love quantum neural networks for some reason. So they want to research how can we quantize neural networks, and I think this is more like a hype question because neural networks are cool. They are the fancy thing in machine learning, but it's one of those things, they have the magic when you're on the outside. But after many, many years of trying exactly that, because I was one of them as well, I think I really realized that sometimes not the fanciest method is actually the one that is mathematically the most logical. And this one is probably a lot easier to link to quantum computing. Okay, I don't want to like speak too long because I already spoke for quite a long time. I'll kind of like go a bit like more, you know, shorter through this one here. Because I just convinced you that actually the first part here is like the important part, because that already does this interesting feature map, and the rest of your quantum stuff, as I hope I convinced you in the introduction, just does linear algebra. So it's a very simple model from a machine learning perspective. However, a lot of work in quantum machine learning goes into kind of this model circuit and thinks about how can we train it, how does it look like, what's a good ansatz, and so on and so forth. There are different ideas of how the structures look like. They're often quite complicated to understand at the beginning. There's absolutely no theoretical reason to use one rather than the other, except from that physicists have kind of used concepts they already know. So for example, this is you know, something called QAA ansatz, or this here comes from tensor networks. So, so at the moment, we don't know what circuit could be the best in machine learning. There's a bit of, this is a very nice study that thinks about like how expressive are those circuits. So for example, just an identity gate maps to one point only. If you have a couple more gates, it might map to more points. So basically, like, you can distinguish circuits in how flexible they are. So that I thought was a very nice study. But is flexibility really like a measure that's good or bad? Because remember, in the end, we want good generalization power. And how do you know if your model has good generalization power? You have to try it. But at the moment, we can't really try things because our simulators can only like handle a few qubits. Our hardware is very noisy and can also handle a few qubits. So this is where I say, like, we really need theory. We can't just like be blind and do this thing. We need theoretically understand what's generalization in our context. Also, those like not the data encoding, but the other circuits all have templates in PennyLane. So you can basically with 2 lines write a really huge circuit where it encodes data and then does lots of processing on the data. You could also actually like as this circuit use a Grover algorithm or an HHL algorithm or like an old-fashioned quantum algorithm, then you would have the more like traditional quantum computing. So the stuff that I'm describing is inspired by near-term, but it totally includes every other quantum machine learning algorithm you can think of as well. And for those of you who are very well introduced into this topic already, this quantum circuit after the embedding, so if you encoded your data, is actually like a neural network that has always the same size of layers and doesn't have any nonlinearity. Why? You can think about a neural network as the kind of being matrix multiplications of different sizes, and the rectangular matrix sizes are defined by how many units you have here in your model. So this is for those of you who know neural networks. But then you do these nonlinearities in between, so it's just this chain. And a quantum computation, as we had it earlier, basically just has like rectangular matrices and no nonlinearities here. So this is why I'm saying like a neural network, quantum neural network is just a very stupid neural network. So I'm not sure if this comparison is actually so useful. The other reason is that this is for those of you who know quantum theory very well. After we embedded our data or encoded our data, and if we can encode it in a way that it's separated, the states of the one data type is separated from the other data type in our Hilbert space, in our space of the quantum states. We know actually which measurement is the best one to do. The best one is actually, it's a bit tricky. There's a bit of fine print, but we know quite a lot about the measurements to distinguish data. So maybe after we encoded the data, we're done. We could even train the encoding. So there's a lot of ideas there that are happening. Another last thing I want to say about optimizers, and that also because there was a question about it, is this big picture here that's a bit daunting. Basically, it just has the message, if you have a long machine learning pipeline, so this could be a neural network that the output goes onto a quantum computer, then it goes onto a neural network, then it goes onto a quantum computer. If you want to train this whole pipeline, what you need from the quantum computer, you need gradients, you need information on what are partial derivatives of our quantum node or our quantum computation with respect to its parameters. And there's really nice research that grew over the last couple of years. I think a similar paper here was from Mitchell that says if the quantum computation looks like this, so this is one of those circuits, you actually just have to run the circuit twice. Once you shift your parameter slightly to the one side, not slightly, but actually by a big amount, and the other time you shift it to the other side, and this S is actually a known parameter. So it's not a finite difference rule, it's an accurate and totally analytic rule for gradients. And what you get out of your quantum computer is now the gradient of the quantum computation. So this opens up a lot of tools for us, because now we can really include quantum computations in pipelines. The question was about quantum natural gradients. So there was a question, can we quantize natural gradients? It has been done in this paper. It's very, very interesting. So to kind of make use of the geometry of quantum states. Conclusion, lastly, I promised you I'll show you some code that integrates the two. Let me just highlight a few things. So now here I import PennyLane and Torch. Torch was the machine learning framework. I define some data, I define a quantum device, and now I define a circuit. And this is now my model. As I said before, like model will be replaced by circuit. The loss is the same as before, the average loss, so it's the same as before. And now I have this like kind of little optimization loop that you know from the Torch and the quantum computer. And what you do here, you literally train data on a quantum computer. So this example, it's not the best practice in coding. I've just tried to code it up in a way so that it shows things. So please don't use this now as, for a thesis or something like that. But this will already be an example of a quantum machine learning model. And to conclude also the PennyLane part of the talk, you see how important it is to make this software, because every little step in here took, I don't know, 5, 6 papers, years, and then a lot of thoughts and meetings and attempts from like a coding team to actually know what elements we need, how we put them together. But like in classical machine learning, this enables now a huge community to try and play with these models without really knowing what's this embedding or encoding, what's this like ansatz and stuff like that. So we hope really that, it invites, as you say, like education is the best invitation, that it kind of like takes away the hard, is still tough, but like takes away the impossible part and gives everyone access to playing with these models and training them. A few open questions for those of you who do PhDs. As I said, I think we need theory. Why? We don't really know if quantum circuits are actually useful machine learning models. By useful, I mean, they generalize well. As I said, in classical machine learning, you benchmark by just running your code and showing that it does well on benchmarking data. Also, that I find sometimes is also like being criticized in the classical machine learning literature, actually. But we can't do these benchmarks because our benchmark data that we can run at the moment is so small that machine learning people laugh about you. And I remember one of my PhD supervisor once gave a talk, and like a classical machine learning guy walked out of his talk when he started like having 4-dimensional data sets and stuff like that. I find it super interesting to think about is the connection between quantum theory and deep learning, because deep learning is really turning upside down what we know about machine learning nowadays, opening up one of the most fascinating theoretical scientific questions. What does quantum theory talk about that? And then there are a couple of other ideas, but you see, we don't know nothing yet at the moment. We have a basic idea of how to understand quantum machine learning, so that's developed. But all those questions about, is there an advantage, is it good? We literally just don't know. So we don't know if those algorithms for quantum computers that seem to be difficult for classical computers are the ones that are good machine learning models. So absolutely no idea. So this is why we need more theory. Okay, and that's it. There you find PennyLane on this homepage. There's a whole lot of demos and examples and tutorials there. Yes, I hope you're still there and awake after talking for so long.
Yeah, thanks. Thank you, Maria. Maybe Aishin, you can share the question answer.
Of course. Thank you so much for the talk, Maria.
Are you able to share, Aishin?
I can't. Maria, could you stop sharing?
Oh, sorry. Oh, yeah. That
Okay,
makes things
thank
easier.
you. Sorry. I can't choose the, yeah. Okay. Now we collected some questions from our participants for you. So I would like to start with the first questions. How would you recommend a computer science students to study quantum computing?
Cool. Yeah, I get this very, very often. And I think a couple of years ago, it was almost impossible. And now it's just, there's so much out there. I would always go into the software framework. So if you go to Qiskit or Circ or also PennyLane, as I said, they try to create a community. So they put a lot of resources in there. And I think once you have programmed it, you understand the basics. You don't need to go through all the physics to understand quantum computing, I think.
I think the second one is like the first one is related. Maybe we can have other questions about job opportunities in the field. The third one, besides the normal physics coursework, what skills are needed to enter quantum information research field?
Yeah, and again, so this answer really changed. So don't listen to people like a couple of years ago, they really didn't know what's happening. I think with any skills you can go in there. And we had a student in first year who learned quantum computing in 1 month, and he wasn't, you know, smart, but like he was a normal person. And it depends on what you want to do. But for the experimental stuff, for the software related stuff, there's nothing you need except from interest and persistence as usual.
Another question about the research. What are more practical use cases of the domain? I think this person wants to ask, we can't access quantum computers. How can we learn research without accessing them?
Yeah, I would use the simulators, to be honest. Unless you have to, I wouldn't use the real quantum computers anyway. So imagine you have a quantum algorithm of 3 or 4 gates and you constantly get the wrong answer out, and then now you have to make sense out of it for a paper. So I think actually like not using the hardware at the moment is quite a blessing if you can avoid it, and just use the simulators to understand what's happening.
Okay. Could we get a practical example of using quantum machine learning? Is there a tutorial could you provide for beginners?
Yeah. So, I mean, you saw on the slide, so you can just like copy that and write it down. And then also, so obviously I'm talking about PennyLane a lot because I know a lot about it, but if you go to PennyLane.ai, there's literally 30 tutorials and most of them are related to papers. So whenever you see an interesting QML paper, we're trying to implement it in a tutorial to show you this is actually doable. And sometimes it takes us quite a long time actually to understand what people are talking about, because code doesn't lie, right? Like you have to know what you're doing. Yeah, so I would really check those out. I think they will help you.
I think the following question is somewhat related to that. Do you recommend any paper or book in machine learning in quantum?
Yeah, so
and quantum machine learning, and we know you already have one, supervised learning with quantum computers.
Yes, you might want to wait a bit. So most of the books, there was also one by Peter Wittek, and he, so most of the books were written, I mean, the discipline is really growing, and now you can see like a couple of things that people are publishing more and more on. When this one was written, it was not yet clear what's actually the trend. So even this like thinking of like old school and near-term quantum computing wasn't entirely worked out yet. We're working on the second edition, so at the moment, yeah. Anyways, if you need the book, and I think it's very expensive, send me an email and then I'll send it to you, but it still has a couple of mistakes and I would like to really update it.
Thank you. And the following question, what I understand is preparing supervised learning sample in quantum programming. I think he would like to ask preparing data for supervised learning in quantum computers, maybe?
Yeah, if the question is about data samples, maybe I can frame it in a way that it would actually be very interesting. So as machine learning, classical machine learning have their data sets and they always test their algorithms against those data sets. So MNIST, you might know. And there's a group of people led by some colleagues at Google who are thinking about making this like canonical benchmark data set for quantum machine learning. So there might be some interesting stuff coming out of that.
Okay. What should one learn to think about PhD in quantum machine learning for coming from quantum background?
Yeah. So let me answer like that. Obviously, this depends on what you research on, but what I think I should have done, I learned from textbooks, which at the beginning you have to do, but I thought machine learning was what's in the textbooks and what's in code and, you know, the stuff that you learn online. But machine learning is actually a scientific discipline and it has papers and it has really high level research that is extremely interesting. So what I wish I had done is much earlier start reading papers. And I think there's no discipline in the world that I know where papers are written so well. So the authors of most machine learning papers really struggle to make it understandable for others. So it's a joy to read them. So I would go to NeurIPS, which is one of the biggest conferences, just take the featured papers there, the ones that are, you know, won a prize or something, and read through them and get a feeling what people are actually discussing. It's completely different from what we think, actually.
So from a person who has a MSc in quantum algorithms, she wants to ask research opportunities in Xanadu for.
Yeah, so also the next question, I think, so we don't have like official internship programs where every year we take like 10 people and so on and so forth. This is partially due to the fact, unlike like IBM or Google, we're a very small company and you have to spend a lot of time and money on these programs. We take, so the best way to get into any startup is to be relevant, obviously. So it's very often if you already work in a topic and you're expert in it and you love it and you have a vision in that, I think no company will ever say no to you. So I think the steps are the other way around. It's not so much to go to company to learn. I think for that, you'd rather go to the bigger companies like Microsoft has a, you know, where they have the more formalized internship programs. But for the smaller startups, it's really cool to become extremely passionate and good at something and then knock on their door and say like, I want to do this at your place. And I think that's a useful strategy there. We don't have PhDs, unfortunately, as well.
This one from our last guest before you, Ronald. Yeah. What application areas does classical ML fail? And would some of those be good targets from quantum machine learning?
So this is an extremely hard question because classical machine learning is almost good at everything. So at the moment, you put a deep learning model into something and it just performs. And so this question, I also thought like going systematically through things and trying to figure that out. And I was never really able. So you get bits and pieces of information. For example, I heard once that breast cancer screening is sometimes not so good, but then often the problems are very domain specific. They're actually not technical problems that you can just abstract away. So I really can't answer that question very well.
Okay. There are lots of problems that can already be solved with classical machine learning methods. Then why quantum machine learning?
Cool,
what's the potential advantage of?
Yeah, I hope are kind of these, I think there are a lot of questions about these advantages, and I think this is fair, because why should someone give us money? And at the beginning of quantum machine learning, you can imagine it as being a bit like people, I sometimes say, like, people discovered an island and then thought like, oh, there must be gold on the beach, so let's start digging, and everyone was excited. And now I think it's the next step, where we think like, we look at the island and think like, oh, there's actually natural resources, it's actually beautiful here. Like, there might be a lot more to discover, but it will take time. You don't get rich immediately. So I think we had this like trying around and understanding of what quantum machine learning is. Now we get a step back, and now we have to understand, to analyze it, to get tools to analyze it, and then we can go back to the question of advantages again. Otherwise, we just drown ourselves in this provable advantage that we will never find, because the field is just not useful for that. Yeah.
Okay. Another question from the same participant. During the NISQ era, most of QML research is expected to be done by simulation. And here comes the problem. Simulation for more than 20 qubits seems to pose formidable computation challenges. What's your suggestion for researchers in the field about our situation?
Yeah, I also have the talk answer that. That's theory building. Like quantum computing has done, but quantum computing has done it for their own needs. We need different theory.
At what point do you think we would have crossover to some quantum advantage? I think this one is similar to others advantage questions, or possibly just parity with classical computing for an application.
Yeah, I think. Yeah, I think the advantage questions. I hope I didn't disappoint anyone, but I think they all have the same answer from my side. Yeah.
Okay. Given the no-go theorems of quantum mechanics, such as no cloning, no addition, how machine learning, which highly relies on those operations, possible?
So that's actually an interesting question. So it's difficult to answer it in all generality, but no cloning, I think, as such, is not is not a problem, for example, for data loading, because the idea of the pipeline is you've got a classical data point, you run your state preparation algorithm that encodes the data, and you can do that as often as you want. You never have to clone your state, you just re-prepare it, right? So there, it's not a problem. It is a problem, though, which I didn't talk about at length, which is this gradient, so the quantum backpropagation. So it's this idea to get gradients out of quantum circuits, because the reason why neural networks are so successful is that they can be trained extremely efficiently. They can be trained in time that's faster than the number of parameters, actually, because in the training, you can share information between like gradients of parameters, and you can't do this inside a quantum computation. So long answer short, I think that there are some fundamental theorems that we can uncover where we say like quantum computation has limitations in backpropagation, but they are not yet clear to anyone, I think.
Another question, how much does it cost for you to operate strawberry fields?
For free, so it's all open source software, and most of you know that open source doesn't only mean it's free, but also it's maintained, it has certain standards, it's under the right license, so yeah. I think most of quantum computing software is free.
Which industries could benefit from quantum machine learning?
Big question. So again, we're on an abstract layer at the moment where we need to get the problem run in general. I start thinking slowly. I have a couple of ideas. So we had a bit of work on, actually that goes back to Ronald's question. There might actually be one discipline, but classical machine learning is getting better and better at this, which is graphs. Graphs are objects, data objects, like a Facebook network of your friends could be, you can do machine learning on those objects. And there, maybe in something like that, quantum computing could be better. There are results that might not, but so it's more like an industry needs to have, so it's not so much this industry or this industry, but does the industry have a certain problem structure? And even that problem structure is not entirely known yet.
I think the first part is what you already answered. And the second, is it mandatory to know classical machine learning in order to learn quantum machine learning?
I think so. Yeah, because otherwise you're just doing quantum computing and you know, you won't have an impact on the stuff you're really doing.
And any likely discussion on QE?
Yeah, first of all, hi to South Africa, which is where I am at the moment as well. Yeah, so just as a background, these quantum variational eigensolvers are those trainable circuits I was speaking about. Actually, the whole idea comes from a field called quantum chemistry. So a lot of what people develop in quantum machine learning, and also, for example, PennyLane, is we have a complete subpackage for quantum chemistry because these two fields and their approaches are very close together. So a lot of it you will be able, the gradients and everything you will be able to use for quantum chemistry and also apply for these variational eigensolver models.
Another question about the career. Does quantum machine learning have higher job prospects in the near future?
Yes, so I don't know about in a couple of years because obviously everything gets hyped and then dies down. But I can speak about myself that after my master's, I applied for, I already worked in quantum neural networks and stuff in my master's, but I applied for jobs locally, but quite a lot, and I got rejected everywhere. And after my PhD, I had now quantum machine learning under my belt, and there was a very new field, and all of a sudden there were so many job offers. So in my personal life, I can say it has really helped my market value, and will probably also still for a couple of years be like that.
Another question, what do you think is the most advantage quantum computer could yield to machine learning?
I think these are all, yeah, the same questions about advantage. Yeah.
Okay. The other two, I think they are, I would like to summarize them because they're all asking about the research opportunities, or what do you think about them in the industry and the research sites?
Yeah, so I think that this question that I try to sketch about generalization, for example, can quantum variational circuits, so these trainable circuits, can we say something about if they generalize well? I think this is a question for research. Then also there's a lot of, in the training routines, like the gradient calculations, so there's a lot there. So basically every little subfield in these circuits are actually relevant, and there's a lot to uncover. Yeah.
Is quantum machine learning at a stage where it can be applied like convolutional machine learning?
Yeah, no, I hope after the talk you realize no. And also you saw that the code examples I made, I always had like 1 or 2 or 3 wires or qubits. So this is where we're at. So absolutely not.
Another question about combinatorial optimization problem. As simulated with the, I couldn't be bifurcation machine to solve it. They read about that. And since it runs on classical machines, it can optimize really large matrices easily. What is the size difficulty of matrices solvable on a 128 qubit computer?
Yeah, so that's a very specific question. I think I can't answer that because I don't know what a simulated bifurcation machine is. And obviously combinatorial optimization problems, that sounds very much like a quantum computer I haven't spoken about, which is D-Wave or
Yes.
D-Wave based systems, which is a simulated annealer or quantum annealer. So I would look there. They're also very interested. Actually, D-Wave was one of the companies whose employees or whose team was kicking off quantum machine learning at the beginning with a couple of other groups. So they should maybe look into that and their work.
Any comments on quantum machine learning on for the aerospace industry?
Yeah, I don't know. I know there's also a question later on high energy physics, and I think we wrote a bit of a review, but all these applications, we have to do our homework first, which is a lot more general than the applications.
And also there is a finance. I think they're basically the industries asking.
Yeah, I think a lot of people would give you different answers. They would immediately say, oh, quantum computers are good at linear algebra, so we can solve this and this problem. But I'm very skeptical because yeah, you know, part of my job is to find applications, and it's extremely hard. And an application for a scientist is also not very often an application in real life, because, for example, there was this in quantum chemistry, this vibronic spectra and, like, you know, molecular calculations you can do on a quantum computer. We call this an application in our papers, but actually, like, when you ask a chemist in industry, this is so far away from what they need every day. So also think of this as there's a big spectrum of what people think is an application.
Could we explore the circuit design of training parts using graph theory approach with quantum walks?
Would be cool. I haven't heard much about quantum walks entering the field, but I started off with quantum walks. Actually, I wanted to join quantum walks and biological neural networks, and it completely didn't work, because quantum walks are, you know, they have this reversible structure of, you know, conserving energy and stuff, and it was hard to understand what they can do. But please go ahead and do it.
Next one is, I think this person collected some sensor data from some robots and want to use quantum restricted Boltzmann machine and apply deep learning approaches. I think they try to access the wave, but I think he's trying to experiment quantum deep belief networks also. Is there anything in PennyLane or Xanadu would give example of, or?
So quantum restricted Boltzmann machines are very much, it depends on how you use them, but I think one of the proposals is training them with samples from a quantum annealer. So this would be very specific to D-Wave. But maybe I can say something in more general about if you're kind of a student and you need something, and then there are all those companies and groups out and you need something from them. At the moment, the atmosphere in the companies is that we are so dependent on users and on, you know, also young people get trained, we can recruit one day. So at the moment, the idea is really, you try to be really nice to people, and you want to support everyone everywhere where you can, and also make your tools free. And D-Wave also has a lot of, like, options to access. So what I want to say is, don't give up. Send interesting, short and informative emails to a couple of people. Just try. And I don't know of a company who wouldn't kind of make a plan, unless they are just so busy that they can't really, like, think about it. So just keep trying to find the right person who gives you that access. That's the short of it.
Are you aware of any recent works on specifically quantum reinforcement learning?
Not of recent works. I lost a bit overview, I have to say, because there's so much out there. But my colleague Vedran Dunchko was super active on quantum reinforcement learning, and people in Innsbruck. So their papers, as I said, they are a bit more like old school quantum computing, but they have very, very interesting results in there. I think he hasn't published anything recently on it, but it also doesn't harm to pop him an email. Yeah, Vedran Dunchko, he's in Leiden now, I think.
Any thoughts about recent process of quantum generalization of natural gradient descent?
Yeah, that was, so there is a version. I hope you noted the paper.
From the context of quantum computing, what is the broad, I think they are talking about breadth of our actual technology to reach the kingdom of quantum machine learning?
The kingdom of quantum machine learning. Yes, no, that's very cool. Yeah, so we can totally do the small scale experiments, and you know that this near-term version of these training circuits was actually designed for near-term technology. But then in real life, so the one problem is usually in quantum computation, you would have to run a circuit once or a couple of times if you want to estimate the results somehow. But in machine learning, you always have these training loops. So you have to run your algorithm a lot of times. So we always have this constant factor of 1,000 or something. So actually things like, for example, how fast is the control, you know, electronics is really important, or how long do you queue in the cloud before it's run? So I would say at the moment, there's no, you know, there's no barrier for quantum machine learning with our current hardware, but we need a slight bit more resources than everyone else, I guess.
Another question, can we propose quantum version of each classical machine learning algorithms, and is it sure that will be more accurate than classical one always?
Yeah, so that's definitely a no. So first of all, it's tricky to say what's accurate. So do you mean basically the training error goes low or the test error goes low? So the accuracy of your machine learning model. And then also this was actually what people did at the beginning. So they quantized every possible algorithm and just sought for like advantages. But yeah, there were different results. You have to read them all to really like estimate them properly. But I think quite an interesting story was the one about where they used the Harahazdim and Lloyd, so HHL algorithms to speed up linear equations. So almost every machine learning algorithm was translated into an algorithm where you have to solve a linear system of equations, which means you have to invert a matrix. And then they used this quantum algorithm. And some of them, as many of you might know, was then dequantized. So people realized, oh, this, there's actually a classical algorithm that under all the assumptions you make also runs in that time or close to that time. So I think it's, as I hope I've pointed out, I think it's not the right approach to think like that, but rather create something new that we are good at.
Another one about computer vision networks on quantum computers. Is there a way, standard way, we can build them and get higher accuracy?
I was just thinking, which question do you read? I think that the person means CV was this continuous variable model.
Continuous variable model. Oh, sorry, man. I'm sorry. I thought that that's computer vision.
No, I see. When someone uses abbreviations, it's the ones for. No, but this is a very beautiful question, actually. So when I say that quantum computing and neural networks don't fit, there's actually a quantum computing model where they fit, and that's this continuous variable model. It's a bit more complicated, and not many people know about it. So this is why I didn't talk about it. But
sorry, we didn't know about it.
that's cool. But we actually have a paper from a year back or so that shows that those continuous variable quantum computers, they are almost by default neural networks. So it's very easy to map neural networks onto them. It's just there the question is, what's the advantage? So we can run them a bit differently, but we really couldn't pin down why should someone do that, except from speed, maybe energy consumption or something, but we don't know what the quantum adds here.
Are you familiar with the paper, Do Artifacts Have Politics? No.
No, but I don't know if there's one, if political property means what social implications quantum technologies have, then I actually think about this quite a bit. And so I don't know what social implications they will have one day, because with any technology, you never know what it's used for. It's probably used for a lot of things one day. But it has actually quite a lot of social implications nowadays in the community of scientists, which is that young people get rich with quantum computing. So they go to companies, like internship salaries are through the roof, and they can be like part of Google, getting the Google salaries, for example. And that really changes a bit, because all of a sudden you're part of a emerging technology network that gives you a social responsibility. And I have often the feeling that not many people understand that they have social responsibility that comes with this power and with this money, with this recognition. So there's something interesting happening in the community at the moment. And if we want to know what's happening, we can actually look to machine learning, because that happened to them on a much bigger scale, maybe 10 years ago. And we should be careful actually to maintain what we like about honest research as well, and not commercialize everything. But yeah, so that's just a comment.
When and how can we expect quantum computers to have an active role in experimental particle physics at experiments such as?
Sure, I don't know, but I think for that, this QQ sector should be discovered, because the cool thing about quantum machine learning there would be you've got a quantum experiment, and then you want to analyze the data. So maybe there's some way to feed some of those particles you study into a quantum computer. I don't know how this would look like, but this will be very interesting.
Another question about the access to quantum machine learning. Classical machine learning is possible and accessible. How quantum machine learning will be possible and accessible?
I think that was, yeah, similar to questions before.
Okay. Does PennyLane have Q state like quantum harmonic oscillator states as well, additional to binary qubits?
Yes, so I think they're called Q modes usually. Yes, it does. So what you have to do, there's a default device, which is called default.q Gaussian, which is a, so basically what the question is, like this continuous variable, the CV quantum computing, can PennyLane do that as well? And yes, there are devices, there are gates for that. And you even have a plug-in to Strawberry Fields, which is obviously the full-blown quantum CV simulator.
Is Xanadu looking at making PennyLane a more high-level language, more object-oriented rather than the text user interface?
I'm not sure what object-oriented means, because we obviously use object-oriented programming. So if you say something like def.state or for example, most of those objects are actually classes, and you can work with those. So obviously the user-facing part is maybe not so object-oriented. So maybe this is where the question comes from. So I'm not sure how to interpret this, but in terms of, we would really like PennyLane one day to be, you know, really on the scale of Qiskit, to be a full-blown quantum simulator that you use for anything, not only for quantum machine learning.
Another question about asking examples in continuous variable circuits as well, especially now that we have got the QML.
I'm so happy that all those continuous variable questions come. Yes, so I refer again to this continuous variable quantum neural network paper. I think that's quite interesting. It hasn't been, you know, it hasn't made some big news or something, but I think it's a very neat approach. And then what we at Xanadu do a lot is look at so-called GBS, which is a Gaussian boson sampler. You can understand this as being the near-term device of a continuous variable quantum computing. And we have a lot of quantum machine learning applications and ideas of how to use it, and the entire software for that. So I don't know if anyone else is working on it, to be honest, but we have done a lot of work in it, and it's very interesting actually. And I think CV computers can do different encodings, and I'm starting to uncover at the moment, but this is not published yet, that it might be more powerful as per se, because it encodes data in a different space or a different way. So.
There's a feedback operation involving to mitigate the loss factor. However, due to high measurement times as opposed to the coherence times and the lack of reset operations, how feasible is it on the NISC devices?
I think that's this question of like that not only running the algorithm, I mean, that takes usually a short time, but you need to factor in the whole control loop and stuff like that. And in so this depends really very much on the hardware. Up to now, Rigetti's devices were really quick because you didn't wait in a queue or something. So that was working extremely well with PennyLane. With Qiskit, like IBM Quantum Experiments, you have to sometimes wait, and some of the stuff I try to simulate, you can just not do it because you wait just too long in this overhead. I'm sure that in the next years this will be better though.
I'm not sure if this question is repeating. Is there a standard way of creating neural networks in quantum circuits?
Absolutely no, there are hundreds of ways. And this is why I'm saying like no one has really come up with a dominant method that's so convincing that this is the one, I think.
There is one question. A person learned Qiskit, quantum computing framework. What PennyLane can give advantage of them?
Yes, so Qiskit, I think they're also starting to have sometimes like community developed facilities for quantum machine learning. But at the moment, if you code something in Qiskit, I don't actually, correct me if I'm wrong, if maybe in the last months or weeks something happened there, but you can't really optimize the circuit and you can't really use all the machine learning functionality. You can't integrate it to PyTorch and TensorFlow. So if you want to use the Qiskit devices, but you want to do quantum machine learning, you should think of using PennyLane with Qiskit.
Another participants thanking for your presentation, Giovanni. What do you think about evolutionary strategies to learn circuit architecture and gate parameters?
I was always thinking about that, and actually in almost every machine learning conference that I went to at the beginning, I always ask the people, why do you use gradient methods all the time? Why don't you use other optimization methods like evolutionary algorithms? And they all just say in high dimensional spaces, and machine learning optimizes in very high dimensional spaces, without gradients you're lost. You just don't find your minimum. I don't know. If everyone does the same thing, there's probably a good reason not to do it. But in this case, it seems like you need gradients as information.
Another question. You mentioned the goal of machine learning is generalization, which is different from speed up. But can one think here improvements in sample complexity, time complexity,
Yes. Yeah, I think it's with respect to shame, you get all the abbreviations. So yes, so I'm not sure I understand exactly right, but like, so yes, there are also improvements, not only generalization, but also sample complexity, which means you get maybe the same results, so the same quality of a model, but you use less data. There's a lot of interesting theoretical work from actually not also quite a bit longer ago on sample complexity that shows that that we don't get exponential speed up very likely from quantum computers in terms of how much data we use, but we get quadratic speed ups. And I was talking to one of the authors of those papers recently and asked him, like, can't we use that? Can't we make quantum machine learning algorithms that just use quadratically yet less data to do the same result? And yeah, he was also interested. It's probably not so easy, but there's interesting research topics there. And also with my rant against the speed ups, in the end, obviously, if they are kind of connected, generalization and speed up. So because if you can, or at least for quantum computing, if you have a model that generalizes much better, but you don't have a speed up to classical computers, you can just implement it in a classical computer, and you might become famous in classical machine learning, but you haven't found an application for quantum computers. So in the end, somehow there needs to be a speed up, but I think we should free ourselves from constantly only thinking about that.
Which of the available quantum programming languages or libraries is the best for implementing QML algorithms?
Yeah, so the earlier stage quantum machine learning algorithms, so where they use like HHL and Grover and you know, the traditional quantum algorithms, I think that you could use any library. I think Qiskit is not bad because I think they've got a lot of you know, high-level abstractions so that you don't have to implement Grover search, but you just, you know, call a routine. I think the variation circuits, there are at the moment 2 libraries. There's PennyLane, which I presented. And then since a few months or a few weeks, there is TensorFlow Quantum, which is a quantum extension for TensorFlow. So in opposition to PennyLane, you can't use any devices and any machine learning framework there, but you are tied to TensorFlow and to Google's quantum simulator. So, but obviously, if you code something that's more specific, it might also be better for certain cases. So those 2 I would know now.
Can you give more information about quantum neural network models and why you think they are not as good as parameterized circuit models?
Oh, first of all, there's actually something that could be very confusing. People since a couple of years start calling parameterized circuits quantum neural networks. So this is even more confusing because this is just a name, but the like in older research, quantum neural network was a name used for a quantum model that really reproduces what a neural network does. Quantum circuits don't. Like, it's just like, you know, to really find those activation functions and linear transformations. So this just as a side. And why I don't think they are as good as parameterized circuit model, I'm not sure about the as good as, but it's just, let's put it like that. We've got the parameterized circuit model and we can try to understand it now, and we can try to understand it as a neural network. So maybe I mentioned, you can understand it as a linear neural network of lots of layers that have the same size. But I don't know what advantage you have from this. So I think you should understand parameterized circuit not as neural networks, but as these kernel methods, these support vector machines. So they're not really like competing against each other, but it's just, it's kind of like, how do you interpret your parameterized circuit? Do you try to make it imitate a neural network, which is really hard, or you just take the name, which then doesn't make a lot of sense, or you interpret it in terms of another model, which is a lot closer. Sorry, this was a lengthy answer, but I hope I was maybe clear.
Another, how much does it cost on average using the real quantum device, and which one would you recommend?
So I don't use hardware a lot, but my colleague has for now half a year tested all the devices, and it's funny because there's really trade-offs you can see. So the ones that I know of that he experimented a lot with is Rigetti's hardware and IBM's hardware. And Rigetti's hardware is faster and easier to use, but the fidelity is a lot lower, which means you have a lot more noise. Sometimes computations don't make sense at all. Qiskit is a bit slower. I think both of them are free of charge. Sometimes companies have this like network of people, so you have to register somewhere and then you can access it. But as I said, I think if you ask very nicely, you should be able to. I think there's, is there the Muslim singing in the background? Is it the sunset?
Oh,
That's so pretty.
It is on. Yeah. Can classical machine learning be improved with quantum random number generators, let's say for weights initiation?
I wouldn't know. Would be an interesting question. For weight initialization, I don't think so, because it's actually not so important if they're really random. You just want them to be like kind of about arbitrary and then not too close to zero. So interesting question, but I don't think for that purpose.
Okay, I think this one is our last question. Any comments on Silk programming language, which is developed especially for quantum computing?
Okay. Any comments? Yeah, I don't know that one, but there's so many. I really lose track. There's a very a cool place or cool organization called the. I saw a talk on that, and one of the guys is actually a student of mine, but the Open Quantum Software Foundation. It's a Canadian-based one. So if you check Open Software Foundation Quantum, I think you'll find it, and they compare, so their goal is to compare a lot of the languages and stuff, and there you'll find a lot of information on those, but I can't tell you a lot about Silk.
I think you made some comments about that a couple of minutes ago. What do you think about TensorFlow Quantum?
I think it's super cool, and it's so what's really interesting about, so this is now a bit technical, but so what's really cool about a TensorFlow is a framework that can backpropagate through computation, so to speak, so automatic differentiation. And now what it can do, it can backpropagate through the quantum computation. So in PennyLane, we also have a couple of devices that can do that, but to build something directly into TensorFlow is obviously super cool, because TensorFlow has, you know, one of the biggest machine learning communities already in the world. So yeah, it's quite cool. And we're also like friends with the team, and you know, there's a lot of like very friendly competition, so to say, in the field, because at the moment we just want to get tools out and want to get people interested, and you know, we help each other usually quite a lot there.
And now I can see with the comment, then this one is really the last question. When will Xanadu's quantum computer be accessible by the public?
Yes, so very soon. We're a bit delayed due to Corona, but we will like soon open basically for, you know, a network of partners, so basically like a beta testing phase, and then yeah, it won't be too long until also like other people can first of all maybe apply to use the quantum computer and then be accessible to the public.
Thank you so much.
Watch the space, yeah.
Okay, thank you so much.
So Maria, thank you. We told you our question answer sessions are quite long. Thanks,
it's nice you go through it so thoroughly.
Thanks really staying longer with us. I mean, there are different kind of questions, and maybe it's also opportunity for many people to ask a question for an expert. So we still find it valuable. And I also thank to still there are 100 people are watching us. And thanks again for this nice talk and also answering all these questions. Also thanks to Aishin for moderating the questions. And Maria, yeah, if you want to say something at the end.
Yeah, great. I hope I see you all on the next Quantum Machine Learning Conference or in the space. And feel free to find my email address online. If you have questions, especially if they're very specific, then drop me an email and I'll try to answer.
Okay, thank you very much.
Thank you very much.